Okay, so I want to state when operators must commute and when they need not commute. And to do that, I'm going to want to introduce one more idea. So let me introduce that first, and then we'll come back to the statement of these two operators. Okay, so here is t, here is x, there is x, there is t. And I'm going to consider 2 points. I'm going to consider a point over here. Let's call this point 1. And I'm going to consider a point over here. Let's call this point 2. So the space-time position of point 1, x1 mu, this will be t1 and x1. The space-time position of point 2, this we will call T2 and X2. And then what I'm going to do is I'm going to study the vector Y mu, which is the difference between X1 mu and X2 mu. And I'm going to want to get a Lorentz invariant quantity. So I'm going to take Y mu and I'm going to contract it with Y mu. Okay? So this is the quantity that I want to study. So let's write down what that quantity is. So Y mu is equal to T1 minus T2 squared. So that's the time component of this vector squared. Okay, maybe I should write down what this vector is. It's T1 minus T2 and X1 minus X2. And Y mu will just be the time component squared minus the space component squared. Let's write it like this, squared. Okay. So now let's consider 2 points. A point here and a point there. Now, let's put on the light cone. There is the light cone. There is the light cone. This is 1 and 2. If we look at these 2 points, well, everywhere along this blue line, the distance that you travel is equal to the time that you take, because this is a world line of light, and we've said c is equal to 1. So for this, these 2 points, 1 and 2, you can see that this time difference is bigger than the space difference. The time difference is bigger than the space difference. Okay? Because of that, this quantity Y mu will be greater than 0. And because it's more time separation than space separation, we call this time-like separated. Okay? And between these points 1 and 2, you can travel between those 2 points. To go from 1 to 2, you are moving slower than the speed of light. So you can travel between time-like separated events. Okay, so we call a time and a position an event in space-time, and we're saying we can travel between time-like separated events. This, if you look at this situation, where we've got 1 sitting there and we've got 2 sitting there, then in fact, if you looked at Y mu, this would be T1 minus T2 and 0. You know, they're at the same spatial position. And for this case, if you calculate Y mu, this is obviously greater than 0. It's just equal to T1 minus T2 squared. And you can obviously go from 1 to 2. You just don't move anyway. You just let time pass, and you will go from space-time event 1 to space-time event 2. Now let's consider a situation where here is t, here is x, Here is our first point, 1, and here is our second point, 2. So if we now draw on our light cone, there's our light cone. So if we look at what is y mu, remember, it is the time difference squared minus the space difference squared. The time difference squared between the 2 points minus the space difference squared between the 2 points. Now here, that's the time difference between the 2 points. That's the space separation between the 2 points. So this little distance here, this would be telling you what T1 minus T2 is. And this much bigger distance here would be telling you what x1 minus x2 is. So y mu, which is T1 minus T2 squared minus the mod of x1 minus x2 squared, well, this is going to be less than naught, because the mod of x1 minus x2 is much bigger than T1 minus T2. When y mu is less than naught, we say that these 2 points are space-like separated. Okay? Space-like separated, you can see this is more like a spatial separation than a time separation. They're mostly separated in space rather than time. And here is a perfect example of 2 points that are space-like separated. They really are at the same time, but they're separated by some space difference. So I hope that gives you some intuition about why we call these 2 events space-like separated. So we could say the events are space-like separated if y mu is less than naught. Okay? And if 2 events are space-like separated, you can never move between them. Okay? Because to get from 1 to 2, you'd have to move faster than light. So you can never ever move between events that are space-like separated. So if we take a look now with this new language at this situation over here, we would say that the origin and A, this is a case where the 2 events are space-like separated. So OY and OA are space-like separated, whereas if we look at OY and OB are time-like separated. And the previous rule that we were arguing for, if 2 operators are space-like separated, so not even light can travel between those 2 events, then the measurement of one operator cannot disturb the measurement of the other operator. So space-like separated operators must commute. Time-like separated operators need not commute. Okay, so let's just record this conclusion. This is actually what I wanted to conclude. So let's clear a little bit of space. So we've said that special relativity forces us to consider fields. Quantum mechanics forces us to consider operators. So the first conclusion that we can make is that in quantum field theory, so in relativistic quantum field theory, observables must be operator valued because of quantum mechanics, fields because of special relativity. So in quantum field theory, observables must be operator valued fields. And then the next conclusion that we have reached is that space-like separated operators must commute. two operators which are space-like separated. That means signals cannot travel between them. The measurement of those two operators cannot disturb each other. But if measurement of one operator does not disturb the measurement of the second operator, that means those two operators have to commute. This is the conclusions of this chapter. In quantum field theory, observables must be operator-valued fields, and space-like separated operators must commute.